integrability. Jules, maybe most of you know, is working here at IPhT, and is a mathematical physicist working in quantum integrability, many body systems, and so on. So thanks a lot. By the way, so if you are from outside the institute, we go for lunch after the lecture. And so just stay at the entrance. We will give you some card that you can use at the canteen. Okay. Thank you.
All right. So thanks, and thanks for having me here, and thanks for showing up, even though it's kind of maybe still holiday or maybe not. I encourage any questions, especially from the non-senior people, because that's really the point of this course, that people learn something about this topic. So it's meant to be very pedagogical and so on. Also for people watching online, either live or later on, please ask or email me with questions if you have them. So what I want to talk about is this outsider, and it looks kind of very technical, and maybe it's a bit intimidating. Certainly to me it was before I started working on it. So the point of the aim of this course is to give an introduction to kind of guide you kind of through this and give you a starting point to really appreciate why this is a very beautiful and nice area, and where kind of maybe the physical intuition comes from in some sets of problems, and that should be a good starting point if you later on would be interested to continue really working on it, or just for general interest. So what I want to start with is just some general kind of context of why this is an interesting topic if you're not already working on it. And before I go there, let's start with, okay, so this notion quantum integrability is not really well defined. It's a kind of a vague name, but I think the way that I want to think about it is the study of models that come from physics, from theoretical physics, with some underlying quantum algebraic structure. That's better. Okay, so models coming from physics that are somehow mathematically very nice, and this is a bit we will get there. So what this quantum algebraic is? It is we will slowly start to see during these lectures. But in terms of mathematics, it's related to representation theory, and in particular of things called quantum groups, which were developed in part because of this field. But physically, the consequences of this underlying structure is that such models have many symmetries, and they are exactly solvable in some sense. So they have exact analytic methods to study things of quantities of physical interest. And so for me, quantum integrable models form a subset of more generally exactly solvable, so exact solvability. And the idea that happens here is that if you're working on a model, then you might be very clever and somehow come up with a way to solve this, like describe exactly energies or things like this. So you might somehow be able to find an exact solution to the model, whatever that precisely means. But that doesn't really give you great understanding. Quantum integrability is one layer deeper. It really comes with an algebraic structure, which is very rich, and this allows you to get this exact solvability. So it's kind of, doesn't only give you the exact answer for what you're looking for, but it also tells you why you have this answer. And so it's a really rich structure. It's also a little bit ad hoc. I mean, if you give me a model, it will be hard to see whether or not it's quantum integrable. I can put it in the computer, and if I'm lucky, then some of these symmetries are really visible in the spectrum, but that's not even necessarily so. So it's not obvious a priori which models would be quantum integrable and which ones are not. But rather, it's kind of like something that once you see it and it works, then slowly you might be able to develop an understanding of why it works and so on. And that's really what we do in quantum integrable systems. And I will kind of illustrate this today and in the coming lectures in explicit models and how historically people kind of first found some results and then how slowly it was understood what the underlying mathematical structure was. And
sorry, how generic is this quantum integrability structure? In the sense that for symmetries, you know, we can just look at the, just for standard symmetries, we can look at the symmetries of a model that somewhat constrains, say, the Lagrangian and blah, blah, and then, you know, we still have some separate dynamics and so on. So can you do the same with this sort of
right, so let me clarify. What I mean here by symmetries is not just that you have like SO3 symmetry or so, but really what I want lots of commuting Hamiltonians. So I wanted kind of momentum to be conserved, energy to be conserved, higher kind of quantities of this type to be conserved. So sometimes we call this a hierarchy or a tower or a big family. Hierarchy, oh, a bit hard. Of Hamiltonians. So there are really lots and lots of symmetries, and in some sense there should be maximally many symmetries. And in the quantum case, this is not, it's a little bit of work to really properly characterize what maximally many means. So it's actually easier to kind of say which underlying structure you want. And then from that, we will get lots of such symmetries. Yes, I know. So it's really kind of, so basically what I'm saying is there's a particular area in mathematics which interplays extremely nicely with with different parts of very special models in physics. And integrability is really the structure of this relation. And we will get there. I mean, this is a bit vague now, but you know, I'll have to give examples to really show what I'm talking about. So that will be the point later on.
Yeah, I guess the question was, I mean, I can understand that you can have some very, very special models which have a lot of symmetry, maximal symmetry, and whatever. That's very good, and it's nice. But can you use this to characterize somewhat more generic models?
Right. So the idea,
or maybe with some weakly broken whatever.
So
I don't understand.
So this depends on the model. In some cases, the model is kind of, the integrability is kind of robust in the sense that you can perturb away from it, and integrability can be a very good kind of starting point, and you can really use this to understand a bit kind of like an area kind of this model in kind of model space. Other models that are integrable are much more special and delicate, and as soon as you vary things, often you kind of completely break this structure. So the structure, it can be very delicate. However, the idea is that, as you know, I mean, so if you're lucky, then in each universality class, you have an integrable model, and you use it to study universal properties. In fact, as I will kind of, well, the whole idea of universality, so that there might be models that have parameters and the physics doesn't really depend on the values of these parameters, comes from an integrable model, namely the 2D Ising model. So then people realize, like, oh, this actually, if you compute thermodynamic quantities, it does not depend on kind of the ratio of two couplings, so it's universal. So this was really an important theoretical step. And then later on, there was another model, the 8-vertex model, which has a different universality class. So also the idea of universality classes come from integrable models. So integrable models really allow you, they're very important theoretical, they might be special, but they're really important to study, you know, at least there are some points that you can really study in great detail and really learn a lot. So this was historically extremely important. And moreover, if you want to learn about phase transitions or universality classes, then you know you can try to find an integrable model in the class that you're looking at, study that, and that's the idea of how they might be useful more broadly. I will talk about other kind of real-world applications of integrable models later on. So even though they're very special, some of them are actually realistic and occur in nature or can be built in the lab, and we'll see that in a moment as well.
Okay, thank you.
All right. So historically, and we were kind of talking about this already a little bit. So historically, there are, in my opinion, but I'm happy for experts to protest, there are 4 main categories of these type of models. So 4 different kind of settings in theoretical physics where integrable models appear. But the first one, well, okay, this is the first one because the first work there happened. So they're called quantum spin chains. So they're quantum mechanical models. They are 1 + 1 dimensional lattice models, so discrete space, and they're quantum mechanical. And one key model here is the Heisenberg spin chain. and that will be the topic of today. And some key names of people that worked on it. So I'll try blue, but tell me if blue is either unreadable or too close to white. So the first person who worked on this is Beta. I haven't seen it yet, but I understand that he also appeared in the Oppenheimer movie because he was certainly very important in that program historically, and he was a great physicist. One of the many different things that he did is take a model, solve it, and this was really the start of the field. And then he went on to do lots of other stuff, but somehow he really gave one of the great impulses to this field. Then other people that worked on it that were quite important were Yang and Yang. And the first of these two, if you put them in alphabetic order in their first name, is the Yang from Yang Mills. Then there's also Faddeev, which you might from Faddeev-Popov ghosts. And then maybe a bit less famous outside of the field are Jimbo and Miwa in Japan. And certainly I should mention here Godin, who is was the French superstar from our local, from here, of course. So these are people that really developed a lot of this theory and were very important. So Faddeev had a big school of people, Reshetikhin, Grinfeld, many other people came from there. So this is sometimes called the Leningrad School. This is called the Kyoto School. So Japan also has a lot of very good people in the field. All right, so this is one kind of, this is the earliest direction. And then a little bit later, the second field came from lattice models, where, I mean, spin chains are also lattice models. So let me clarify that now. I mean, two-dimensional lattice, no time. So it's statistical mechanics, classical statistical mechanics. And so they're lattice, of course, also lattice models. And some models that are quite famous in this class, well, there's the Ising model, to the Ising on square lattice. I put it in parentheses, it's certainly very important, but I'm not going to talk about it. So the type of models which I will talk about are called ICE-type models, or sometimes the 6-vertex model. And another one I already mentioned is 8-vertex model. And these are really the ones that were super important historically for the development of the idea of universality classes, and so on. People that are famous that works on this kind of stuff are Lee, Sutherland, and Baxter in Australia. So they were very important, working mostly on this type of models. Now let me continue on this side. The third class are quantum many body systems. They are also 1 + 1 dimensional, like these spin chains, but they have continuous space rather than lattice. They're again quantum mechanical. And some famous models of this type are the Lieb-Liniger, or delta Bose gas, I think it's also called. And another one is the Calogero Sutherland, or Calogero Moser Sutherland type of models. And as the name suggests, so Lieb was important here, and Sutherland was very important here, and well, of course, also Calogero, but I want to highlight these two guys. And then the fourth kind of pillar, which was also very important, is quantum field theory. Again, 1 + 1 dimensional, of course, continuous, of course, quantum mechanical. And a very important example here is Singe-Gordon. And this was, among others, was studied by the Zamolodchikovs. I'm not going to write it twice, unlike Yang, so I'll just square them. And also Faddeev and many other people. And this was historically, they were important to kind of develop ideas in quantum field theory more generally. So kind of like how you renormalize all these kind of like techniques, because this model is exactly solvable. So you can really kind of develop this and understand whether it works and how to do it and so on. Okay. So what I well, then let me just mention that this is historically where these models appeared. But then, of course, so this is in the first, let's say, up to the 80s or something. People mostly studied this. And then later on, it was actually realized. So you see that these settings are quite, they might be quite unrelated. Classical statistical mechanical models, quantum mechanical, lattice or continuous models, quantum field theories. Somehow integrability appears in all of them. We noticed that the total dimension is always 2. So that's definitely a common feature, and it's extremely important for integrability. This can be actually nicely understood in the context of QSD, but I will not go there now. It's a nice little story, but it takes too long and too far away from where I do want to go. But let me just mention a few applications that are a bit more recent, that might be closer to things that you are working on. So in high energy theory, it occurs in IPhT-TV. Both on the ADS and on the CFT side. Well, in many examples, integrable structures appear and are studied. I'm no way an expert, but here Divina and Ivan are great experts. And, I mean, there are many more people working on this stuff. The next one, so this is n equals 4 generally, right? N equals 4 super Young-Mills. Then you can also look at n equals 2 super Young-Mills theory. And then by work of Seiberg-Witten, classical integrable systems occurred. And more recently, Nekrasov and Shatic really found it also, you can kind of quantum integrable systems occur. And then there are many, many, many more. So there's stories in n equals 1, super Young-Mills. One that I also would like to mention is high energy QSED. So n equals 0. And Grisha in the back here is the expert on that. Then another area is conformal field theory. So Bajanov, Lukyanov, and Zamolodchikov realized that any conformal field theory, you can kind of build an integrable system inside it using the conformal field theory data. And more generally, also the integrable systems are very nice because they're very well under control. So you can really try to study their conformal field theory, their continuum limit, and make connections to conformal field theory. And in that area here, Hubert, Sylvain, Jesper are great experts. Then I already mentioned statistical mechanics, so that's another one. Jesper, Philippe, Francesco, Vincent, they work on this. Then in particular, there's also statistical physics with non-equilibrium. So this is related to things like ASEP and TASEP and so on. And Kiron is a great expert on that topic, and Vincent also works on it. And then the last application, which is maybe more related to the spin chains, for instance, here, are in condensed matter. And there, Vincent and Grégoire, they work on this. So lots of expertise actually on integrability here at IPhT. Now, okay, so integrable systems occur in lots of different contexts. And the key is always that somehow the underlying mathematical structure is the same, closely related. And we are happy to work in, whichever context, and people might have their favorite context, but the ideas are always really going from this mathematics to the kind of physics, using this extreme rigid and hard, rich structure that really allows you to control in great detail computation. Now, the plan for the lectures is the following. I want to first talk about spin chains. So this is today. And we will see that spin chains are exactly solvable. We will not quite understand today why it happens. So this is going to be the motivation to then go towards the integrability. And for that, actually, it turns out that you need to go to these lattice models. So that will be the topic of the next lecture. And probably, actually, we're also going to be sort of in between these two. So really, the connection between them will be the third lecture, I think. And then maybe also part of the fourth. And then afterwards, I would like to, maybe towards the end, so I don't know, 4 or 5, so let me just say 5, we'll go towards some quantum many-body systems and reconnect them to spin chains again, depending on how fast we go. But this is stuff that I'm working on with Vincent and also Divina, and I think it's a very nice and kind of different, but really interesting area, which also is relevant for experiments, so I'll get there later. So this is the plan of the lectures. And this is, of course, very broad and blah, blah, blah. But are there any kind of questions or comments at this point? Are you happy for me to continue? Right. If not, I'll continue. Okay, so that was kind of, I guess that was section 1. I forgot to list, but that was the introduction. So now we will go to less blah 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 and more real things. So now we're going to think about the Heisenberg. And to be precise, X is Z spin chain. So that will be the topic of today. So we imagine, so this is going to be a model for magnetism. So in a magnetic material, so in some metal, atoms are sitting very nicely in a equally spaced in a kind of a nice array. So we imagine a one-dimensional crystal, and we're going to think of it, it's called a spin chain, so because they sit in a one-dimensional array, and actually we will often think of this one-dimensional array to be a circle, so periodic. So we have some atoms sitting on a circle, they don't move, but they have spins. So let's say spin 1/2, jumping up and down or whatever, like this, and they can interact with each other in some way. And they might interact kind of across longer distances or just between neighbors. This depends on the model. So I will call the number of these atoms L for the length of the chain. And I will denote these, we will call these things, we will call them sites. So here's some site L, the Lth atom. And so at site L, we have a spin 1/2, let's say. So I will just focus on the simplest case. So we denote the basis by up and down. And then we have local Pauli matrices. So I will denote by sigma alpha L the alpha Pauli matrix acting at the Lth side. So if we have L particles, then you should take tensor products of these things. So what you do is you have this whole thing together. We have a Hilbert space H, which is C2 with that basis. L times, one for each of these sites. And then the alpha Pauli matrix acting at the Lth side, we just take the identity, L minus 1 times. So we don't do anything here, here, here. Then we take this sigma alpha, and then we do the identity, the length minus L many times. So we see that here we have an operator that acts on L minus 1 plus big L minus small l, so L many sites, so on this space here. And it's just the action of these Pauli matrices at this L site. And I will actually prefer to not use Pauli X, Y, and Z, but instead lowering and raising operators. So for me, I will take Pauli plus, which is explicitly this matrix, Pauli minus, which is its transpose, Pauli Z, diagonal, and I also have the identity. So this forms the basis of all the possible matrices at a single site. And then you can check that they obey the usual relations. So Pauli plus and Pauli minus, they commute to Pauli Z. And Pauli Z commutes with Pauli plus or minus by Pauli plus or minus Pauli plus or minus. And now we have this at different sites. So we just put subscripts K and L for different sites. And then this commutator is only non-zero if we have Pauli matrices at the same site. So lots of little representations of SL2 mathematically. So I think of it as SU2. Okay, so these are the local operators that we will build that we will use to build all our operators and everything else. So then, this Hamiltonian, it is of the following form. So we have some parameter, delta, which we take to be real, and this is called the anisotropy. Anisotropy. And then the Hamiltonian depends on this delta. which is minus sum over L in, let me just take a color to explain in a moment what this means, Z with a subscript L, and then H little l, L plus 1. And this H, it depends on delta, but I will often omit the delta there, of course. And this is what we call the local Hamiltonian, and I just factor out the minus sign because I find that more convenient. And what this here means, these are just the integers modulo L. So what I mean here is that we have periodic boundary conditions, like the picture suggests. So if at some point we find an HL L plus 1, and this by definition is just HL comma 1. So that's what this sum here means. It's a sum over all the neighbors, but periodically. So these are also neighbors. And now this local Hamiltonian, little h L L plus 1. Well, we can write it in terms of these Pauli matrices as follows. Maybe leave a little bit of space here if you're taking notes, because we might want to add something later. So it's Pauli plus at little l, Pauli minus at L plus 1, plus the Hermitian conjugate, so Pauli minus at L, Pauli plus at L plus 1. And then plus, here we don't need an extra space, delta, Pauli z at L, Pauli z at L plus 1, minus, well, identity times the identity, but I'm just going to write it as 1 over 2. So this notation here, note this is a product, but this one acts at side L and this one at side L plus 1. So really this is like a tensor product of two of these Pauli matrices. So you remember the tensor product means that you take one and you put it in one matrix and you put it inside the other one. So we can actually write this as a 4x4 matrix acting at side L, L plus 1. So then it looks as follows. There's a 0, then minus delta, 1, 1, minus delta, and a 0. So it's block diagonal, and I subtracted the minus 1 there to set these two entries to 0. And then this is a 4x4 matrix. It acts at side L, L plus 1. So this notation, just like before, let me write it explicitly. This means that we have the 2x2 identity L minus 1 times. Then we have this 4x4 matrix from there. And then we have more identities, but only L minus 1 times. Because this is already L, L plus 1. And this matrix is written, of course, with respect to the standard basis of kind of two sides. So it's up, up, then up, down, then down, up, and then down, down. That is the basis with respect to which you get this matrix. Okay, so this is the Hamiltonian. So we have this nearest neighbor interaction between sides, not like this, but rather just like this one and this one, L plus 1. And they interact in the same way for each pair of neighbors cyclically along the chain. And there are these terms here. So let's give them some nice physical interpretation. So this here, what happens? What we will do often is we will think of up spins as kind of empty and down spins as a kind of a particle or an excitation with respect to this empty thing. Then for those down spins, these are just a kinetic term. They're hopping between nearest neighbors only. Whereas this part here is the potential energy. So if two down spins are aligned or anti-aligned at neighbors, if two spins are anti-aligned or aligned at neighboring sites, then this gives some potential energy. And here I've just shifted this. So this is so that H delta on the vector up, 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 up is 0. It's just a bit more convenient, so we don't have to kind of carry around some energy here. Okay, so this is the model, and this models magnetic materials. So let's see.
terminology, potential.
So it's like potential energy and kinetic energy. Or yeah, like it's like a discretized. So this is kind of like a discretized. Well, we will see this more clearly later on, but this is a bit like this relates to a discretized second derivative. So you think of this as some kind of Schrödinger operator, but on a lattice. So this is a kind of a lattice version of the Laplacian in some sense. We will see this more precisely later on. And here it's kind of a potential energy, because here you just have two adjacent spins and they interact depending on whether they're aligned or not. Here, instead, you see that what you do is if there's an upspin at side L+1, you make it a downspin, and here you make the downspin an upspin. So it means that you hop a downspin one side to the left or to the right.
You have the harmonic picture in mind.
Right. So that's
fermion and the config is described on
right. So I should, right. So I should actually say, so the picture that I have in mind here is sometimes called a quantum lattice gas with hardcore, because they're not allowed to sit on the same side. Bosons, in fact. But of course, we're in 1D, so you can bosonize from behind. Whether they're bosons or not doesn't matter so much. But formally, if you create a downspin in kind of two downspins, it doesn't matter in which order you create them. So in that sense, it's kind of a bit like bosonic.
The number delta.
Yes.
You defined at the beginning. This I have been late.
Oh no, delta is just a parameter. So this model depends on one.
It's just a real number.
It's just a real number. Yes. We will split. That is right. So it's an isotropy parameter. So you see, if delta is very large, then the potential dominates. So it's kind of like a coupling. It's like a coupling. That's right. Yes. Very good. Okay, and so we think of the bosons, we think of them as the downspins, for instance, doesn't matter. And hardcore is because you can't occupy the same side. So you can either think of this as a model for magnets or for some sort of, well, discretized one-dimensional hopping particle model. And okay, so I want to say something about whether or not this is really realistic, because one thing that's really cool, and it's a development of kind of quite recently, is that this model is actually it's really realistic. This really describes extremely well some things that occur in nature or in the lab. And so let me just make a small remark here about that. So the features of this model are, firstly, it's one-dimensional. So in terms of space, one maybe +1, but I'm focusing on the space now. Dimensional, so it's very low dimensional. So you might complain that this is not very realistic because we live in 3 spatial dimensions. However, nowadays in the laboratory, people have extremely good control using optical lattices and so on, and they can really kind of make confining potentials, which essentially make particles move in one dimension only. It's not completely true, but they can really very strongly kind of prohibit particles to move in any of the other 2 directions. So such a one-dimensional space can really be built in the lab. So for instance, optical lattices. Other things. And also it occurs in nature, actually. So there are some magnetic materials, which of course are, metals or that are compounds that are 3-dimensional materials. But in these cases, it can happen that the spins of the particles only really feel each other in one direction. So it can also happen that interactions are effectively 1D. So this is not, it's not, it's not great. It kind of misses out many models, but actually, or many vertical systems, but it does really correspond to reality in some ways. And these are really developments in the last few decades. And yeah, but it's quite cool, I think. Then the next feature is that this is only nearest neighbor. So the particles can only hop to neighbors, and they only feel each other if they're sitting at neighboring sites. So this is a restriction of the model. It's an assumption of the model. And it turns out to be very good for certain materials. So in fact, one thing which in nature has effectively one-dimensional interactions and has spins that essentially only feel each other between neighboring atoms is, I have to look this up because, so it's a compound called KCuF3. So for normal people, this is called perovskite, cubic perovskite. And this is extremely nice. So I strongly encourage you to look up this archive paper. It's a publication in PRL, I think, 1307.4071. So they've done inelastic neutron scattering on this with this material, and then the neutrons interact via their spins with this material, and they can use this to measure stuff of this material. And what they've done is they've measured certain things experimentally and compared it to results that you get from this beta ansatz that we will talk about later. And it turns out that the beta ansatz really accounts extremely well for the properties of this model. So even though, you know, we're only having a one-dimensional model and we're having nearest neighbor interactions, and actually another thing which is not so realistic is that we use these periodic boundary conditions. And of course, normally in nature, these things are not really periodic, but if you take the length L to be sufficiently large, then you may hope that this is not really important, your choice of boundary conditions. And so it turns out that all these three things really work very well for this perovskite. So this is extremely cool, I think, and I can mention that in this case, delta is essentially -1. And there are, if you're interested, I can give you 5 other names of other complicated chemical things which have delta as -1 and -0.5, and I don't know. So it really occurs in nature, and it's super cool, and they really do experiments, and you know, so even though it goes from mathematics, it goes to reality. Yes.
It's also realistic to have this only along the z direction.
Right. So okay. So indeed. So one thing that you can wonder is why do we make the z direction special? I mean, why did we make one direction special? That it was z is not important, of course, but that one direction is special. So we don't have to do this. So the reason why I wanted to optionally leave a little bit of space here is that what you can do is you can add another coupling, which is called capital gamma. Let me just write this down. So here there's a 1 plus gamma over 2, and then we have to add one more term, plus 1 minus gamma over 2, and then we get sigma plus, L plus 1, plus sigma minus, L plus 1. So we have to add this to the local Hamiltonian. What it does in this matrix is it changes this 1 to a 1 plus gamma over 2. And then there's a, in the complete off-diagonal parts, there's a 1 minus gamma over 2. So this model is also, so now we have a second coupling, which is a parameter, which is also real. And this in general is called the XYZ spin change because it has different couplings in 3 directions. So you can consider it, and it will be more general. It will describe more materials in nature. However, mathematically, this is extremely much harder than if you would have gamma equals to 1. So I will focus mostly on the case, or actually exclusively on the case gamma is 1. And then we get what is called the XXZ model. And you can already guess that if you would also set delta equal to 1, then you get the XXX model, which of course can cause some kind of weird searches on the internet if you don't carefully add some scientific words. But it's a standard name for this model. So we have the XYZ, XXZ, spin chains. And XXX is slightly easier, but really it doesn't matter so much. So XXZ, with this delta, basically we have to do the same analysis to understand it. And so that's why I want to use it. It's nice to have this delta to play around with. But it's not much harder than if we would set delta equal to 1. Whereas, yeah, so this gamma really complicates life. In a very interesting way, of course. Yes?
The perovskite that you mentioned, why people look at these materials?
So, well, so you can actually look it up on the internet. So it looks like a blue, like a blue glass. It's like a stuff that you can touch. And apparently some artists used it in I don't know, a few decades ago to kind of completely dress a room. So it's very cool because he built kind of a huge version of this model in reality. But so the fact that it's interesting is because it's a realization in nature of this model that you might say is a little bit unrealistic because we only have one dimension and so on. So
I mean, maybe it's a provocative question, but if I take a computer and I put a big matrix just this formally. Is this a physicalization of the thing? I mean, I understand, but
No, so I mean, I would like. Well, I mean, that's just philosophy. Maybe it's not my.
I know that it's very provocative.
Well, no. But so what I mean is that even though we make some restrictions that are a priori, maybe make this model kind of like unphysical, but just mathematically nice, and then we can talk about universality and blah blah blah. But in fact, it does describe at least some things that are actually, like actual stuff in nature. So that I think is very cool, because this topic is very technical. So sometimes you forget that it's about real stuff.
The spin of the electron is 1/2.
Yeah, right. But they might actually feel each other at a little bit longer range, or they might. They're probably not going to be really periodic, and they might also be able to hop in all directions. So yeah, so spin 1/2 is the least of the unrealistic assumptions. Okay. So maybe let's see how we're doing. Okay, so let me try to keep this, because this will be the model that we'll talk about all the time. So try to just keep it there. I'm going to erase this stuff. All right. So one thing that I want to do is we talked about this delta. So let's explore a tiny bit. Well, okay, maybe I should say the goal, of course, is to study the spectrum, so the energies and the eigenvectors, and then compute correlation functions and all of this. And the strategy is to do it first for fixed but arbitrary values of L, and then hopefully, well, in fact, one is able to really control the low-lying part of the energies and the correlation functions to such an extent that you can really understand, sometimes analytically and sometimes at some point with metrics, what happens as you send L to infinity, and that's really how you make contact with the experiments. So that's the goal. Now, descending the length to infinity part is really about either analysis or numerics. I don't want to go into either of them. I want to stay with the algebra. So I will stay at the finite but fixed L throughout. So to get some intuition of what this model looks like, let's take two simple limits. So we can just send the delta to plus or minus infinity if we take this Hamiltonian and we divide by delta to make sure that the result is finite. And then we get minus or plus, because remember there was this minus sign in front, times a sum over pairs, and then we just have this sigma z, L plus 1 minus the identity part. So this is if you think about it, the shift is not so important. This is just a one-dimensional Ising model. This Hamiltonian is already diagonal. So in fact, if you just write down, the basis vectors, they're all already eigenvectors. So it's kind of quite a trivial model. It is a classical model because everything is diagonal, so you don't really need to think about superpositions and so on. So it's just a 1D classical StatMech, but not two-dimensional like I mentioned here, but one-dimensional. So it's kind of so simple that it's a little bit boring, but it's also very good because we can easily understand what's going on here. So we have these two possible signs. So if we take a plus or a minus, we can immediately think what's the lowest energy. So which vectors have the lowest energy? So if you have the plus sign there, so the upper sign here, maybe I should say upper and lower. Then the lowest energy is achieved if all the spins are aligned in one direction or the other.
Just a question. Just you have this sign because you divide by the value.
Ah, that's actually true. Yes. Thanks. Very good. Yes. So okay, so all the spins are aligned are the lowest energy here, and then how do you? Well, what does energy come from? So in terms of this, so we can interpret actually this term in another way. What this does is it just counts. So it's the number operator for the number of occurrences of misaligned spins. So each time you have misaligned neighbors, it's going to cost you some energy. So here, everybody's aligned, everybody's happy. So that's good. But we understand now too that the lowest excitations are those cases in which you have, well, you must have something like this. So kind of some domain like this or the opposite. Some domain like this. Of course, these kind of domain walls, they should, since we are in a periodic system, there will be two domains at least. So we cannot just get one domain, but the smallest thing we can do is we can flip in some region all the spins, and so that there are two of these domain walls, two of these misalignments, and this will be the lowest excitation above this ground state. Instead, if we take the opposite side, so let's assume that L is even here, because I don't want to think about frustration now. Then there are also two ground states, mainly alternating. So up, down, alternatingly all the way. Or you could start the other way around, down, up, etc. And in this case, smallest excitations are those cases in which we flip one of the down spins, and then here we have down to click, or the other way around. So we have this alternating like this, and we flip one of the intermediate up spins. So we see here that these are maximally polarized, whereas these have net polarization 0. So these are both models for magnetism, but one of them is ferromagnetism, and one of them is anti-ferromagnetism. So that's kind of nice. So with this, we understand very easily two very special limits of this XXZ spin chain.
In your lowest excitation for the ferromagnetic case, the domains, you could have a larger domain than one.
Here. You mean?
No, for
anti-ferro? Well, so what do I want to do? Here I want to have maximally many misalignments.
But if you flip inside if you flip every spin inside the interval,
yes, so
you still have a,
right, that's actually true, right.
Okay.
Yeah. So you can just have, you have to have kind of two, kind of not domain walls, but the opposite somewhere, but these two kind of can move, that's right. So indeed, so you can kind of extend this, so you kind of have a zone, let's call this, I don't know, type A and this type B. Then what you really have is A everywhere, then a small region with B, and then A again, Or the opposite, right? That's right. So indeed. Similar to here, but here A and B were kind of maximally polarized. So let me tell you, just for your intuition, that if you would do all the computations that I'm going to hopefully talk about today, and you would also do the analysis of sending L to infinity, then you would find the following phase diagram. In fact, you can do this also for finite L. So maybe if so, then I want to take L even, and I'm going to only think about 0 temperature. So we have just a one-dimensional phase diagram. So we have delta, and it can have values from -infinity to +infinity, with some special values at -1, 0, 1. So we already saw. So here we have an Ising, which is anti-ferromagnetic Ising. Here we have ferromagnetic Ising. Here we have this special case, which is called the XXX spin chain, and it is the ferromagnetic XXX. Whereas here there's an XXX chain, which is anti-ferromagnetic. This is not completely clear yet, that it's also XXX, but I'll get there in a moment. And so this whole regime is ferromagnetic. Let me just write it here, and it's called the axial regime, because if you kind of think of the spins as living on a circle, then this delta is kind of somehow like squashing, like squeezing or squashing the sphere in one direction. And if delta is large in absolute value, then it's kind of like a very elongated kind of, something that looks a bit like this. And here as well, but this is also axial. Whereas this here in the middle is called planar. because instead we have something that looks like a very flat kind of squeezed version of the sphere. And this whole regime here is anti-ferromagnetic, this whole part. This one was all ferromagnetic, and here in the middle, this is called paramagnetic. That's some sort of weak version of magnetism. And here we already have a nice, at least in the ferromagnetic or anti-ferromagnetic axial regime, we have some sort of intuitive idea of what the structure should look like from this easing model. And in your mind, you know, delta is going to correct this a bit, but vaguely it will behave kind of like what we have here. So here we're also lucky. At delta 0, there's also a very special model. This is sometimes called the XX chain, because the delta is 0, so it's kind of like XX0. Unfortunately, some people also call it the XY chain, which I think is a very bad name because it's not the XY0 chain. But I think in that case, it just meant that it's kind of like in a plane. Spins are only have an X and a Y direction and nothing else. So, but anyway, it should be called the XX chain. And this is actually very nice. It's also very simple. This is a free fermion model. I guess I'll talk a bit about this in a second. Right. So this is the phase diagram of the model.
Why do you represent by these points?
Well, I mean, it's a big fiction, but if you think classically of the spins, then it's like unit vectors on a sphere, and this delta kind of deforms the sphere. It kind of stretches it or squeezes it along the z direction. So that's the sort of
Can you
fiction.
view it as being the expectation value?
Right. I mean, so they will definitely behave very differently if you would.
So the spins are still on the sphere.
Yes.
They are localized in the poles.
Right. Maybe that's a better way of saying it. Right. So if delta is very large, then spins want to really point up or down. Whereas if delta is kind of close to 1, then the spins are kind of happy to be more generally distributed in points in the XY direction if you really have delta 0.
There is another terminology which confuses me completely. Sometimes they call it easy plane, easy axis.
Right. So people say easy axis and easy plane, but I think just axial and planar is a bit better. Another thing that people use is they call these regimes massive, because the related conformal field theories are massive, and these is gapless or massless. So that's another terminology that is kind of thinking about L going to infinity, which I do not want to do here. So yeah, so there are different.
Massive is a delta larger than 1 in absolute value.
Right. So I can also say this. So delta larger than 1 is massive. And this is massless or gapless or critical. And this of course is gaps. So lots of different names for the same kind of for these regions.
So you need to be sure. What is the other parameter?
Just delta.
The delta is the control parameter.
Control parameter. All right. So sorry. So ferromagnetic, of course. So what you can do is you can take an expectation, but adjust the spin in the z direction. So we see that here they're maximally polarized, whereas here they're average 0. So this is polarized. This is kind of unpolarized, but it has the staggered polarization. If you want to do nearest correlations, kind of one away from each other.
Then you need another of this.
Right. So here you can define this with a second order parameter, and then here you will see that it's still different. Right. So that's the thing that you would measure to distinguish these things. Right. So well, I'm going slower than I thought, but it's good because there's interaction. So maybe before we take a break, let me just give an exercise for. So as I said, so these ferro and anti-ferromagnetic phases, they have a sort of a toy model that we can use to think about, you know, how should we think of the physics here, namely just the one-dimensional easing model. So this intermediate region, which is more complicated and more interesting physically, here also have these special points at delta 0. So here's an exercise, if you want. So for delta 0, what you can do is, well, the goal is to find the spectrum. So all the energies. And you do this by Jordan-Wigner. So there's a Jordan-Wigner transformation. And this goes as follows. So you define, so you notice, if you do some computations with these boundary matrices, then you see that they actually anti-commute at the same, I mean, they have a good, if you think of this as a raising and a lowering operator, then you have kind of good anti-commutation relations at one side, but at different sides, of course, they commute with each other. So that's not very good for fermions. So what you need to do is you need to modify them a little bit. So you still have sigma plus and sigma minus, but you modify them a little bit so that you really get nice fermionic operators. So we define CL to be basically sigma plus L, but with a tail of sigma z on the left. And we define then, of course, C dagger L is, well, the dagger of this, so still the tail of sigma z and then sigma minus. And then you can check that you can also define, if you want, NL, which is the number operator at the site L, which is C dagger L C L, and it's also just the same as 1 minus sigma z L over 2. So this counts the number of fermions, where I now think of the fermions as the downspins. So now I think of them as fermions. So what we kind of typically we're doing now is we're kind of fermionized from what I first said it was a bosonic, supposed to be a bosonic type of gas. So then what you can do, okay, so first check that they obey the canonical anti-commutation relations. So the anti-commutator of CK and CL is delta KL, and the anti-commutator of CK and CL without any dagger or with both daggers is 0. And also check that they obey the following boundary conditions. That if you formally define, kind of extend this formula, and you have a CL plus 1, where you remember that our boundary conditions were periodic for the spins, then what you find is that this is minus 1 to the m times C1, where m is the total number operator. So it's the number of downspins. On the whole chain. Okay, so that's a simple part. Then the second thing is, right? And now there are different levels of at which you can do this exercise depending on how courageous or masochistic you are. So the simplest version is you just take delta as 0. Or if you want to do a little bit more, you can take general delta. Or if you really want to go full on, you can take this XYZ model, which also has the gamma. Maybe I should write gamma and delta. So red, since we had it in red. H gamma and delta. So any of them you can write via these C and C daggers. Then you will the more hardcore version you do this exercise, the more you will see what this model looks like in general. And the nice thing is what you will see is that if you now Fourier transform, so we go to momentum space, so we write PL dagger, for instance, as 1 over square root of L sum over, okay, I'll write that in a second, e to the IPL, and then C tilde dagger L with a P. So this creates a particle with momentum P. And then the sum goes over all the P's in 2 pi over the length times integers modulo L, except that we have this twisted boundary condition sometimes, periodic or anti-periodic. So here I have to put, let me, I don't know, do this in a different color. It is plus a half if m is odd, because of those anti-periodic boundary conditions. So if you express the Hamiltonian in terms of those guys, you Fourier transform to express it in terms of the momentum creation and annihilation operators, then you can, well, read off spectrum at delta is 0. And actually, there's a reward. If you are willing to go red level, then you will see that this still works in the red level as well.
Sorry, what is M?
And what is the total number of downspins? It is the total number of operators.
Okay.
So depending on which sector is, how many fermions you have, you're going to have periodic or anti-periodic boundary conditions. So the Fourier transform has to be appropriate. And the nice thing is that so this, in fact, this XY0, real XY0 model, the XYZ spin chain at delta is 0, you can still read off the spectrum there. So that's very nice. So it's a free fermion model, which is quite non-trivial because we understand in the fermion picture, I didn't mention this, but it's kind of clear that this is kind of like pair creation or annihilation. Yes. So it's a bit richer model. Okay, so the cool thing is that we have this regime. We have kind of a very simple model in one extreme. We have a very simple model in the other extreme. They're very simple in position space. Just the standard basis is already diagonal. And then right in the middle, we have another very simple model, but it's simple in momentum space. So here the ground state would look like a, like a Fermi, like a C. And then excitations are kind of moving, taking one particle inside the C and moving it outside. So it's kind of, in a way, it's similar to this, but then in momentum space rather than position space. And the the XXZ spin chain interpolates between these different models. And one wants to understand the spectrum throughout. Okay, I think it's time for some break. Maybe any questions? Is there any? Okay, so we're going slower than I thought, but it's fine. I think it's good to take it easy and have lots of questions. One thing that I should mention, I mentioned this vaguely here, but I think it's important. So nowadays, what they can do is either with ultra-cold atoms or with trapped ions, they can really use these, well, I don't know, optical lattices, and I have no idea what they do, but they can really put atoms very precisely in a lattice and so on. So they can really engineer these type of systems, and they can really engineer these Heisenberg spin chains. They can control the value of delta. So they can do experiments where they prepare the system at one value of delta, and then they can kind of suddenly change the value of delta and see what happens and so on. So they have really extremely good control over this. And this is in particular important because these are also precisely, this would be called the quantum simulation of the Heisenberg XXZ spin chain. And this is done by labs that are at the same time really working on quantum computers. So this is precisely the machinery that people use to build quantum computers with these trapped ions and so on. So also there, these models are good. They really might pertain to quantum computing as well. So anyway. Okay, so before we go, so what the goal is to understand the spectrum of this model in all the other values of delta that we haven't treated yet. And for this, we're going to do something which is called the beta method. But before we get there, I want to do a little bit of thinking about the symmetries and kind of the physical kind of quantities that are in this system. So let's do this. So this was part 2.1, I guess. The Heisenberg XXZ chain. So here we get 2.2, if you like numbering. So the symmetries of the model. So, okay, so for the first part, let's kind of make the model slightly more general. Let's say that we take H delta and we add or subtract, doesn't matter, H times the sum of Pauli Z everywhere. So physically, orange was my physical color. This is an external magnetic field, a longitudinal external magnetic field. Of course, a similar question to before arises. You could put this magnetic field in any direction, but to preserve integrability, unfortunately, we have to put this longitudinally. Otherwise, it's you can do numerics and interesting things, but not integrability. And if you think about this in terms of these quantum, these hopping particles, then this is like a chemical potential. So it kind of favors some filling fraction that you can tune with this parameter h. And in fact, it's known in this phase diagram, you can extend it to include this value of h. But now I want to just, for a moment, include it because there's another little exercise. So the first two symmetries are very simple, so they're just two parts of a little exercise. So define, let's say, U, because it's unitary, to be the product over all sides of Pauli x at that side. So Pauli x, I haven't defined it, so I should actually give it now. I can just, let's do sigma plus at L and sigma minus at L. That's Pauli x. So this operator, what it does is it just globally flips things. So it reverses up and down. So this is called the global spin flip. And what you can check, so that's the exercise, is that if you conjugate u delta h, sorry, this Hamiltonian by u, and u is its own inverse, so that's also easy. You get the Hamiltonian at delta, but with minus h. Right? So it really flips all the spins. So this Hamiltonian that I wrote down before doesn't change at all, and you just change the sign of this constant h from. So that's the only reason that I put it here, so that we can actually see what this thing does. Also, this commutes with the Hamiltonian, as we will see in a moment. So this is a good thing. Second part of the exercise is we define a second operator, which we call b. This is now not the product over all sides, but over every other side. Let me write L is 1 up to, and then the integer part of L over 2. Right? So this part here, this is a bit unfortunate. This kind of L floor looks a lot like capital L. But it's a slash L floor, capital L over 2, slash R floor. And then what we do is we're going to do sigma z every other side. So this is kind of like a staggered way of kind of measuring the spin z, let's say. Maybe. And now let's assume that L is even. Then what you can check is that if you conjugate just h delta, I don't want to, now this magnetic field has had its role, then what you're going to get is minus h minus delta. So this is a nice operation because it tells us that, you know, here I fixed sign in front and then I allowed for all values of delta. And I was talking about plus and minus 1, and I was already mentioning that delta is minus 1 is also xxx in some sense. This is the reason why it's similar to the delta is 1, because up to the overall sign of the Hamiltonian, you can reverse delta by some unitary transformation. So the spectrum is the same, and of course this minus sign in front kind of flips the ferromagnetic and the anti, it flips the spectrum upside down. So instead of being up, up, up being favorable, now up, down, is favorable. Or the spin flip.
You confuse, in the first case, you use sigma L plus, sigma L minus.
Yes.
In the second case, you use sigma Z.
Yes, so they're different. There's no confusion there, I think. It's just different operators. No. So this is not a staggered spin flip. This is just some sort of staggered something with sigma z. Yes, right. So you can sort of physically, this is like a rotation over pi of all the spins, whereas this is just something else. It's just some useful operator. It's a simple diagonal operator, and it's extremely nice because it tells us that we can restrict ourselves to this sign that I put in front and consider all values of delta, positive or negative, at the same time. By the way, we can also give a kind of a more hardcore version of this. If you take L is odd, then here you get with empty periodic boundary conditions. So sigma plus or minus L plus 1 or minus sigma plus minus 1, the sigma z is unaffected. But the symmetry between delta and minus delta is really special to, if you want to not change the boundary conditions, it's very special to play even. But if you don't really mind putting a little kind of twist, we call it, then you can do this for any length. And the operator is the same. That's why I put carefully the L floor and R floor. Okay, so that's one thing. All right. Next, more important, is what I call partial isotropy. So it means that we have a U1Z, let's say, symmetry. So define SZ to be the sum of a half Pauli Z at all sides. So this is really this magnetization operator, and the magnet is this kind of it's closely related to this M that I had here. So then, what you can check is that for all values of delta, SZ commutes with this Hamiltonian. This, by the way, is very special for this gamma equals to 1 in terms of the x, y, z parameter. So this is the reason why x, y, z is so much harder than x, x, z. So maybe we can gamma is equal to 1. So what this means is the following. It means that we can diagonalize. Diagonalize H delta per m, which is the same as that m, is L over 2 times the identity minus this total spin z operator, and this is just the number of downspins. So we can fix the number of downspins, and then we restrict ourselves. The Hamiltonian preserves this sector, so we can just take linear combinations of vectors with this fixed number of downspins. So that's a bit better because we don't need to take general linear combinations, but we can take only certain linear combinations in our consideration. So now we're going to write down in its useful this thing called the coordinate basis. So inside this sector of the Hilbert space, we have a basis, and it's just a good way of labeling them. And this notation is not super common, but I think it's very good. So we're going to build a vector which has m integers, and then here I'm going to put a double wrangle, just to indicate that if I have something with this stuff, then these integers mean the following. We flip a downspin at positions L1 up to Lm if we start from this vector, right? I think in physics we have a kind of a habit of, denoting anything by a ket, but sometimes it's a bit annoying because then I have to interpret, if it's a ket of L, then it means something different than if it's a ket of a P or whatever. But then if I want to set L to 1, then I don't know anymore if it was L or P that I set to 1. So I think this is better. Now I can just, actually write down numbers in there if I want to. Note that, of course, to really get a basis, I have to restrict myself to positions of these downspins. I can just order them from 1 to L on the chain. So then it's really a basis. If you like a little bit more, if you're a bit more representation theoretic minded, then what we're doing is we decompose the full Hilbert space into a direct sum of H, I will denote them H sub m, although the standard mathematical notation would be HL minus 2m. So these are weight spaces. And in physical terms, I want to call this the m particle sector, or the m magnon. So what's going to happen is that this H delta is block diagonal, one block per m. So if I take m is 0, there's only one vector which is 0 downspins. So we can there's first going to be a little 1 by 1 block. Then if I have one downspin, I can put it at L different positions. So here I have an L times L block, and so on. And eventually I'm going to get an L choose M times L choose M block. And this is going to be symmetric. So towards the end, it's going to look like this again. And we have zeros everywhere. And we want to understand the spectrum and eigenvectors, eigenvalues of each of these blocks separately.
What do you mean by H of L minus 2?
This here? Oh, well, in mathematics, usually you write weight spaces like this, right? So it's kind of like V of lambda. But in this case, it's just SL2, so lambda is only a single number, and this is it. You can also write it if you like GL2 better. It's L minus M, comma M. And then for highest weights, M should be at most L, safer there and so on. But this was, I will just use this H subscript M. So it's not really important what I meant by what's here. Okay, now there's a way, so I'm going to spend a little bit of time on this because I think this is usually not done and it's extremely nice. So you can really draw the structure of this Hilbert space, and I will add stuff as we go. So let me explain how this works. So I'm going to draw the Hilbert space, as a number of dots, and each dot represents a basis vector. And the basis vector may or may not be an eigenbasis of the Hamiltonian. So the goal is to describe each of these dots as an actual eigenvector of the Hamiltonian that we have. But we will do this slowly, kind of to really kind of we will be able to say we're now looking at this vector here. It works as follows. So let's draw a grid where here I'm going to draw my M. So we go from M is 0, 1, dot, 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 down to L. And concretely, my L is 4. So, I mean, when I'm going to draw it, so there's one dot that has 0. So remember, this was the number of downspins. So there's at least 0 and at most L downspins. There's only one dot which has 0 downspins. So actually, we know what this dot is. This is just a vector up, up, up. Then there are L different vectors. In my case, that's going to be 4, which have 1 downspin. So they could be, for instance, these coordinate basis vectors, but those are not eigenvectors of the Hamiltonian. So I would like them to be something else. Then here in my example, so we go down. So there's 0, 1, 2, 3, and then 4. So maybe I should do it nicer. And then this picture looks like this, and then there are actually 2 sitting here. So this is the structure. So now, how do I know this? Well, let me remove this block diagonal structure. Because on this axis, we already know that here we have L choose M. This is the size of these sectors, right? So here, there's a 1 by 1 block. Then here, for M is 1, there is an L, well, there are L dots. And then eventually you get L choose M of them as a function of M. So we can actually draw this. If you think of the binomial as in terms of gamma functions, then you can actually draw it. And it kind of is this enveloping curve like that. Right? So that somehow what controls this shape. And if you would increase L, then this shape looks more or less the same, but you get more and more and more dots inside of it. And I would like to understand better what the structure of these dots are. So firstly, this fixed M means that we consider so fixed M is a single row in this picture, right? So M is kind of tuning which row I want to talk about. Very good. We also know that we can, if we take the middle here, this is sometimes called the equator, which occurs at M is equal to L over 2, which may or may not be an actual value of M that happens, right? Depending on whether L is even or odd. Then flipping this picture like this is precisely the action of conjugation by this operator U there. Right, so I take a vector here, action is, well, or action of U. By U. So in particular, of course, we know that this guy here is just a down, down, down vector. In my kind of fancy notation, I could maybe say that this is the empty set coordinate basis vector. This is 1 all the way up to L coordinate basis vector. And now here I'm not going to write here because we'll get better information later on. But here, for instance, I have, for example, these denotes the vectors L coordinate basis vector for all the different L's from 1 to big L. So does it make sense, this picture? So I haven't really told you what the dead dots are exactly, but we're going to make more and more precise what these dots are. And it will help us visualize which parts we understand and which parts we don't understand. Also, we can already say, by the way, that our first eigenvector is just this up guy. So H delta, I already mentioned it before, is 0. So it's a bit of a boring one. And of course, its spin flipped is also one of them. By the way, the spin flip, it allows you, of course, it's enough to just understand all the dots up to this equator, because then we get everything else from spin flip. So by spin flip, symmetry suffices to take m at most equal to this equator.
For the moment being, your dots do not correspond to energy levels.
No, not at all. No. It's really just the eigenvectors of the Hilbert space. So I just drew 2 to the L dots, and I'm going to organize them and label them in more and more precise ways. So I'm going to kind of, assign quantum numbers, if you wish, to my dots. That's what I want to do. I want to really say each of these eigenvectors is going to be precisely this one. That's the goal. And whether or not I succeed will.
Sorry, when do you use the word eigenvectors?
All right. So at the moment they're not eigenvectors, but I want them to be. I want to think of these dots as the distinguished bases of the Hilbert space, which are actual eigenvectors of my Hamiltonian. So this dot I know. This one I can really say this is an eigenvector. This one I don't know yet, but it's easy. We're going to do it very soon. These are going to be harder.
So you're going to specify
I'm going
the
to tell you.
vectors, and then at the end you will be able to say they are the eigenvectors.
Right. That's the goal, of course. We want to compute all the eigenvectors and the energies and so on. So that's where we're going. But now at least I can say, I want to know what this guy is. It's a bit more concrete than talking generally about eigenvectors. So I'll add some information to this. So as we go,
That is the generations.
there will be. Well, it depends. So that's the next point, basically. I'm going to. Let's first remove these discrete symmetries. I think they're simple enough that we understand them. So then the next one. All right. So sometimes degeneracies may occur, and here's an important case where that happens. So the isotropic, I will write stuff related to isotropic in blue. So there's an isotropic point. So what we can also define is we can define these ladder operators, S plus and S minus, which are just the sum of the local Pauli matrices over all sides. So they flip at all sides the spin in one way or the other way. So these are, if you wish, SQ2 ladder operators. A physics language or a mathematical language are just SL2, a representation of SL2. So actually you can compute now commutators. So S plus, S minus commutates to twice SZ, because I put this half in front of SZ. And SZ commutates with S plus or minus with a plus or minus. And these operators do not commute with Hamiltonians normally. However, if delta is 1, so this is the isotropic point, then S plus and minus commute with that Hamiltonian. So what this means is that if we found an eigenvector, then we can apply S plus or S minus to it, and we will still get an eigenvector, and it will have the same energy. In this case, this will lead to degeneracy. And so, in fact, these degeneracies, so let me in my picture draw in blue, in the isotropic case there are degeneracies. So what happens is, you take this up guy, and you can exon it with S minus. So let me connect them by a blue line to kind of indicate that you can lower. And then we actually explicitly know what this is. In my notation, it would be the sum of all the L's, because you just flip a spin at one side. So this vector we know in this delta S1 case. And all of these have the same energy. Similarly, if I would be able to find this one, then I can get these guys. And likewise here, and likewise here, and in this case, they're not connected, right? So those would correspond, the length of these strings would correspond to degeneracies that you find in your spectrum. There are actually more degeneracies that we'll get to in a moment, but these are some. So in this case, here, it suffices to find psi such that, well, I want them to be eigenvectors of my Hamiltonian, and I want them to be annihilated by S plus. And physics, mathematical language, these are highest weight. Because the SZ is half the weight. So let me mark these in red, this condition. then in my picture, the highest weight vectors are this guy, this guy, this guy, this guy, these two. So those are the highest weight vectors that I want to find. Right, and one of them we already found. It's just the sum over all the spins, just one. Okay. Maybe in physics language, you can kind of think of this as a Goldstone. So what happens at delta S1 is that the spin, the Hamiltonian is completely rotationally invariant. So here we chose to start from the up, 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 up thing, which is a vector which has spin kind of pointing maximally in the z direction. But if you're rotationally invariant, then you can just move it around and it has the same energy. So you can move infinitesimally, and that is what the action of S minus does, and it will have the same energy. So it's kind of like a flat direction in your sort of energy landscape. So these are corresponding Goldstone.
Are you assuming delta equal 1 here? Or?
Sorry, S? Delta is 1. So this is for delta is 1. That they have the same energy. Of course, I can draw these lines whenever I want, but they have the same energy only at delta is 1.
Okay, so your strategy, you wrote back with
right.
such
a this is true. Yeah, right. So here is in the blue case, in the delta is 1 case. That's right. And a little remark, which is kind of useful, it's kind of related, is that if you would take this local Hamiltonian, H L plus 1, and I now set delta as 1, then I just get the matrix 0, 1, minus 1, minus 1, 1, 0. And you can check that this is just 1 minus the permutation of the spins L plus 1. This is the spin permutation.
About the connection with representation theory here is really because delta equal 1 is special because of it has really the same.
Right. But of course, I mean, I can do the decomposition always if I want, in terms of these blue lines. But whether or not these are eigenspaces of the Hamiltonian, that depends on delta. So whether or not things related by blue lines here, I mean, I can always start from this vector. I can always act on it with S minus if I want. But whether or not the result is an eigenvector, that depends on delta.
But sorry, do you mean your delta equal 1 case, you are applying the strategy to the standard method of representation theory?
Right. So then I only need to find the red ones. But the point is that in the beta ansatz, I mean, we will do everything for general delta. And we will at the end see that, okay, if delta is 1, then some special things happen, and it suffices to only look at certain vectors, which I can characterize in terms of the beta ansatz. So it's not a very important thing, but I think it's nice because, for instance, this allows, I mean, it gives some extra structure that you can use to think of the Hilbert space. But to repeat, whether or not this structure is relevant for diagonalizing the Hamiltonian, that depends on the value of delta. Okay. Can I remove SZ? Okay, so this was a very special point. This is not true. So we will actually.
Sorry, just going back on this
Yes.
the lines. You said U is acting like a mirror.
Yes, it does.
Can we see what V does?
No, V relates different values of delta, right? So it kind of changes your model. So this is the structure of the Hilbert space. It's not really. I mean, it may. I want it to organize it in a way that's related to the Hamiltonian. Well, in a way, you saw that what V does is sort of, well, it doesn't do anything. But what it allows you to do is it allows you to swap delta and minus delta, and it also is related to changing the sign in front of the Hamiltonian. So what somehow this sign relates is whether. So if remember this ferromagnetic regime, then the most important vectors are kind of those on the extremes. Whereas in the anti-ferromagnetic regime, the most important ones, or more generally in the axial regime, these are the most important vectors, and these are the lowest excitations. Whereas in this middle region that we had, which disappeared, the pyromagnetic region, the planar region, the center here, the middle is the most important. So somehow what this V does, conjugation by V, is kind of saying whether the extremes or the middle is the most important in terms of low-lying excitations. So it's information about the Hamiltonian. But at least the picture is nice because I can kind of, I can tell you what G somehow is related to. Another symmetry, which is kind of clear, I guess, is homogeneity, so translation invariance. So let me define an operator G on the Hilbert space by telling you what it does on the basis. If I take some M, I'm just going to shift them 1 to the left. So L minus 1, and here I have to be careful that I do modulo L. And then, well, maybe I should write L minus 2, L2 minus 1, not Ln minus 1. Okay, so it just takes the downspins and it moves them cyclically 1 to the left along the chain. Clearly, this Hamiltonian is invariant under this. So G H delta G inverse is still H delta. This is true for all values of delta. So we can actually simultaneously diagonalize H delta and G. Now G is actually, well, finding the eigenvalues of G is not so hard, because what you notice, of course, is that G to the L is just 1. If I shift everybody all the way around the chain, nothing has happened. So this is just 1. But this completely constrains what the eigenvalues are going to be. So what this tells is that the eigenvalues are of the form e to the I p, where p must be 2 pi over the length times some integer, which is defined only modulo L. So this whole thing is only defined modulo 2 pi because of the prefactors. And this, of course, physically is the momentum, the kind of the lattice momentum, to be, because it's a discrete shift by 1, and this here is momentum quantization. Which is good because we somehow have a system on circles. We expect it to be a moment, and it's translational variant, so we expect the momentum and we expect it to be quantum. So this is how you do it. And this G in particular, so now I would like each of these dots not to just to be an H eigenvector, but also to be a G eigenvector at the same time. And this is nice because G at least gives us a little bit more information. So this actually fixes M equals to 1. I guess I can remove the coordinate basis. Maybe I should just really leave that definition. So now I'm going to basically tell you the results. So it's kind of the semi-exercise is just to check everything. It's very easy. So check that if I define, now I'm going to write, I don't know if it's good notation or not, but it's P with a tilde because it's somehow the Fourier transform of the coordinate basis in the M is 1, so 1 downspin sector. So this guy is 1 over square root of the length, sum L is 1 to L, so all the sides, e to the IPL, and then the single downspin inside L. So this is just the Fourier transform, as I said, of the coordinate basis, and this thing here is just a plane wave in physical terms. And you can check that this has momentum P, well, has momentum P. I mean, maybe I should have called this P total momentum, and here it's a parameter P, and its total momentum is equal to the parameter in there, which of course has to be quantized according to our rule. And since G, well, it's easy to see that eigenvectors of G will be orthogonal. And moreover, so that's kind of something to convince yourself. All of these vectors are going to be orthogonal for different P's. Moreover, the number of them, well, I just count the number in here, is equal to L, which is also equal to the dimension of my M equals 1 sector. So here we had L dots, and now I found L dots. They're eigenvectors of the translation operator with different eigenvalues, so they're orthogonal, and moreover, they are, well, the energy you could compute, but we'll do this later. So this is not part of the end. So energy later, which I guess will be next week. So now I can start adding some stuff in my picture. So much. So here, in fact, note that if you would take p equals to 1, then this plane wave disappears, and I just have the sum over all the things up to some normalization. So it's still this vector. So actually this vector, even though here I got it by applying the lowering operator, it also appears as a momentum zero magnum. So this Goldstone mode is a momentum zero excitation, which has the same energy and the same momentum as the original state. By the way, the up also has momentum zero because it's invariant under translation. So now actually I can understand all of these. So better, here we take them to be precisely our p tildes. So these guys here in this row, we understand all of these dots. There are indeed L of them, and they're labeled by their momentum. So if I wanted, maybe I should have written this in orange. And then I can now say that this column here has p total equals to 0. This column here has p total equal to 2 pi over the length, dot, dot, and then the last column is p total equal to, well, 2 pi over the length times L minus 1, which, by the way, modulo 2 pi, I can also just think of it as minus 2 pi over L. So these two, they're kind of the same, but they move in opposite directions. In particular, actually, they will have, we will see next time, they will have the same energy. So this is another degeneracy in the spectrum. These two guys have the same energy, but they're distinguished if we further take into account their momentum. So energy, comma momentum is a better way to label the spectrum. Okay, so that's kind of cool. So now we understand this part of the spectrum up to here. But at some point we get M is 2. In our picture it's at the middle, but that's of course not the important point. This is the part that we don't understand yet. So now actually you can of course think, okay, this momentum operator is pretty cool, so I can try to understand what it means for the spectrum. And it's kind of it's an optional exercise. This is kind of fun combinatorics, so you can really think about in the 2 Magnon sector, think about which possible momenta can occur. And what kind of happens is that the momentum is related to periodicity, right? If you have some momentum, then it means that your eigenvector has some periodicity. So if your eigenvector has no periodicity, I mean just L periodicity, then your momentum is going to be 2 pi over the length. But if your eigenvector has kind of it might have a periodicity which is just a divisor of L, and then it will have some other momentum. So you can kind of think about if I have this spin configuration, blah, 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 you can count how many each time. So each spin configuration, you can think of how many am I allowed to kind of boost this to this momentum or not. I can take linear combinations like this here, and then sometimes it will be 0, and sometimes it will not be. And in this way, you can actually do the combinatorics, but it's not super useful. So it just tells you that in here, you will have so many times these momenta, so many times these momenta, but they're still going to be dots which have the same momenta. So it doesn't completely tell apart all the different vectors. So the lesson is, but not M, well, not M anywhere in the middle. By the way, maybe to come back to this, so these blue lines, they connect things that have the same energy only at delta as 1. However, they will always have the same momentum. So that's kind of another kind of thing that is useful to think of these blue lines here. They're kind of useful because I already know at least of all these dots what the momenta are going to be. I do not know yet what the momenta are going to be here, but at least I know it in the first part. So here, P dot, bit more work. It's combinatorics. It's related to the necklace group, representation of the necklace.
Anyway, you know, P dot be always multiple of pi over. But so another security for M equal 1, you are good because you have just by diagonalizing G, you find L different eigenvectors, all non-degenerate. So, and basically, you know from that famous speeds, right? But for m equal for m larger, you don't you have degeneracy of a spectrum of V.
That's right.
So do you know
That's right.
for a specific eigenvalue, do you know already how many?
Yes, that's that's a solution to the exercise that I didn't write down. So you can do it with combinatorics,
Okay, so that's
but it's not super easy. I guess I know this, so I know very well how to do it, but it's a lot of experience and what I'm actually doing is I know that there's another model which also commutes with G, and its spectrum is much easier. So that's what I would do. But and since that's only about G, I can that's fine. So in that case, I can write it on. So that's the model that I want to talk about in the last lecture. It's called the Haldane-Shaftesbury switch. So here, the energy, you can really write down the spectrum completely explicitly. There's a very simple way to label all the states in this very simple, and then you can kind of trivially compute their momentum and their degeneracies as well. So it's kind of a very roundabout way of computing momenta, but that's my way of solving this exercise.
Is it a way just by setting delta to 0 and
right? So that could be another way.
That,
yes, that would be another way. Actually, you can take delta 0. Then, of course, pre-fermion models, you excite the momentum or not, and you can also just combinatorics. But then you have to count how many ways are there to add up to this number. So anyway, there's some combinatorics involved. But the point is that even if you've solved these combinatorics, you still haven't found eigenvectors of Hamiltonian because they're degeneracy. They're from ms2 onwards, there will be different states with the same.
It's related to the Bolia theorem or something like that? Counting the action of translation or something. I mean, you want to count patterns of up and downs, which can be related by equations.
Yes, I mean, it's really action. Yeah, right. So it's a kind of some simple representation here of a discrete group. And it involves, Euler's totient function, so some greatest common divisors. You have to, the periods have to divide, then depending on whether they do or don't. Yeah, so you can you can do it. I've done it explicitly for ms2 at some point, and it was kind of nice. And then I was like, okay, I know in general, in principle, how to do it in general, but I'm not going to do it. Okay, so then maybe one more symmetry that I can add to the picture. I wasn't planning to, but I'm already running behind so much that I can run behind a little bit more. It doesn't matter. Because it's useful symmetry to know. So finally, there's parity, also a discrete symmetry. It is defined. So let me call it capital Phi. I don't know. I'm already using P for this permutation, which will appear in later lectures. So I can't really use P anymore. So Phi it is. So it acts on the coordinate basis by just reflecting. So it is a reflection through the center of the chain. So it's L minus Ln plus 1, L minus L1 plus 1. Okay, so I flip all the spins. Of course, here I order them increasingly. So if I want to order this increasingly, I have to reverse the labels. And then you can check that this indeed is precisely what it does. And you can check then that parity preserves conjugating by the parity, which of course squares to the identity. It preserves the Hamiltonian for any delta. But the parity, if you translate this G, if you reverse the G, then you invert it, which makes sense, right? If I rotate one direction and then I kind of flip all the spins, I kind of reverse the order of all the spins, then it's kind of the same as having rotated the other. So in particular, not so pedagogical, but I'm going to make another box here, which is connected to that box. So phi squared to the identity, so its eigenvalues are plus or minus 1. And so we have two types of space. We have things that are sometimes called parity singlets, and we have parity doublets. It's also called parity even and parity odd, related to the sign that you get. And so since conjugation by parity inverts the Hamiltonian, the translation operator, it sends P to minus P, right? So what it does is, in general, if you have some p total, it will group p total and minus p total, which of course is the same as 2 pi minus p total, if you want to work in 0,2 pi. So that's a parity doublet. But sometimes these two numbers are actually the same. Namely, if p total is equal to 0, or if p total is equal to pi. So if your translation invariant, or if you get a sign, if you translate by one step, then parity will preserve you. Otherwise, it will send you to your kind of mirror image in some sense. So very good. So now in my picture, we can also see what parity does, more or less. In this case, it's small enough to really think of it. So here, this is a singlet. These two are swapped. This is what I talked about before. So they are degenerate for the Hamiltonian, but the same for momentum. And the reason but not degenerate for the momentum. And the reason that I knew it is because I knew that there was going to be parity, which is going to relate stuff. And this is generally going to go like this. And then in this case, length is even, so there's one in the middle, which is at momentum pi. This guy is momentum pi, the one in the middle for even length. And then these here, well, they're more complicated. So they may be singlets or doublets. So it's related to what their moment. If you know their momentum, then you know the answer to this thing. Or you can first think whether there should be parity even or not. But anyway, so here, p dot and parity are both a bit more work. Okay, but anyway, it's sort of good. So for instance, for x, z, these dots, they're not just s minus. If they should be eigenvectors of h delta, they're not going to just be. I shouldn't really take these applications of s minus, but I still know how many, which momenta are going to occur, what the parities are going to be, and so on. So it's a bit useful, but not so useful. Yes.
In the case where a state is invariant under parity, you can still get a minus sign, right?
Yes, is that true?
It would give itself, but
no, if you're really invariant under parity, then you should have eigenvalue 1 under parity, right? So parity should just fix you.
Yeah? Don't you have states under parity?
State which is changed, I think.
So psi could go to minus psi?
Yes.
Yeah, but that has momentum pi. Right, so that can happen. That's precisely this one. So this is when it's invariant.
Pi or 0?
Pi means that if you apply parity.
That's moment. Maybe I'm wrong, but I thought
Maybe I'm wrong.
Momentum 0 and pi,
Yeah.
you have in each case
Uh-huh.
odd and
Okay.
even states under parity. You could have momentum 0 and odd, momentum 0 even, momentum pi odd, momentum pi even. That's what I mean.
Okay, I'm not going to answer this right now, but I'll think about it and
I think I remember it's a trick which Haldane kind of used to see if some model is integrable, but I don't remember.
Okay. I'll think about this and comment on it next time. On the spot is.
We even have doublets which have t equals 0.
Yeah, well, but do I think of them as two singlets or?
Maybe not in this model, but in principle you could have two things related like that.
Okay, right. Well, sure. So but that would fall under this case. That's
Sure.
okay. Yeah. Okay. Right. So I said parity is sort of mildly useful. So, okay. Very good. So now, so we have all these symmetries. So we have, we always commute with spin z, so we can diagonalize per row in this picture. We always have the spin flip symmetry, so we can go up to the equator. That's enough. If delta is 1, then it suffices to only get the top L choose L over 2 many states, but for general delta you have to find everybody in the equator and above. We were lucky that some of the symmetries gave us a little bit of this stuff, but certainly there's a part, kind of the bulk here. My picture was small, but this gets bigger and bigger and bigger, and that's really the challenge to solve, to understand the spectrum of that part. And so, yeah, okay, so where am I going to write this? Okay, isotropic was sort of incidental, so to find m equals 2 eigenvectors from 2 onwards, we have to be smart. So far it was just using symmetry. This was kind of the easy part, but now we have to use really kind of skill or art. And I think the best way to be smart is to listen to somebody who's smarter than you. So what we're going to do is we're going to follow beta. And this leads to something called the coordinate beta. So I'm not going to really start it now because I won't have so much time to do it, but I can say a tiny little bit. So this is the very start of section 3, coordinate, beta, and that. Coordinate is because we will use this coordinate basis. Or actually, I call it the coordinate basis because it's the one I can use for the coordinate ansatz. That's it's the same. Beta here. Ansatz means kind of like, so beta was very nice. He had the sort of the physically motivated, and we'll see next time how this works. He said, okay, let's try to find eigenvectors of the following form, physically motivated. And then he could show that it works provided, so you're going to parameter. So really the idea is the following. Idea is physically motivated clever parameterization of the eigenvectors. Well, of let's say would-be eigenvectors. And then you show they're true eigenvectors if the parameters obey a system of equations, which are called the beta ansatz equations. Just going to beta ansatz equations. And then you can easily, the energies are also parameterized in terms of these same parameters. So the beta ansatz equation, so the beta ansatz, what it does is it reduces the problem of diagonalizing some Hamiltonian block by block by block to the problem of solving some set of equations. And the reason why this is extremely nice, I mean, a priori you gain maybe not so much, but the reason why this turns out to be extremely useful is that firstly, these equations have nice structure. So you can kind of classify solutions which behave in certain ways, and you can understand, and this has a physical meaning. So it really has a good physical way of parameterizing things. Moreover, numerically, for low enough length, you can do this, and it may be or may not be more efficient than numerical diagonalization. So at the moment, I mean, my Mathematica skills, this is more efficient, and mine are actually pretty good even for the numerical diagonalization. But so numerically, I can, for x, y, z, I can, if you really fix delta to a numerical value, I can maybe find all the energies numerically just by restricting to these sectors and then just asking Mathematica to diagonalize. I can go up to, I don't know, maybe length 20 or something like this. So pretty good. But these beta equations, certainly I cannot solve all of them for length 20, but they give you much more detailed control of eigenvectors, and they immediately allow you to read off the energy, the momentum, and kind of physically meaningful quantities, even if you didn't want to write down the explicit eigenvectors. And moreover, which is something that I guess I will tell next time, is you can really nicely characterize what the ground states and the localized excitations are. So there are certain solutions to these equations, and you can really cleanly characterize them. They might be all real or have one pair of complex conjugates, parameters, and they have good physical meanings. And this turns out to be, this is precisely what these people who compared this type of stuff to experiments, that's what they did. And they had to solve only some of those equations, and they had very good control with the help of some numerics and so on of this stuff. Moreover, if you send the length to infinity, then rather than solving these equations, you get some integral equations, and you can kind of work with densities of parameters and blah, blah, blah. And you can here really use this to compute exactly, although not rigorously, energies, their leading finite size corrections, and some other kind of observables that are relevant. So that's what I meant by exactly solvable. So the Heisenberg spin chain is exactly solvable because Baker found a very clever way to parameterize its eigenvectors, and this is super useful for not to understand everything about the model, but it gives an extremely good understanding of physically most important properties of the model. What time am I supposed to stop?
Whenever it is a good moment for you.
I think.
I mean, the end it's elastic.
Yeah, the end is elastic. I mean, but this is very dangerous because I can go on 5 hours.
I'm also elastic.
You can.
If you do coordinate better than that.
Exactly. Arbitrary.
No, yeah.
Okay, so I think this is good. Next time I will just recap the findings, but now this is the philosophy. So at least we understand the model. We have some physical intuition of this model. We understand a bit the representation theory of the model. I can also, by the way, well, I can say some kind of like, I can tell you in terms of representation theory what this is, but I don't know if it's useful. I don't know. If you don't mind, let me take like 2 minutes to kind of go very fast on some representation theory, which I think is super nice. If you don't understand it, it's not important, but if you do, then it adds a tiny little bit more structure to the picture. Okay, so what have I actually done in terms of representation? So if you're a mathematician looking at home or whatever, then what I've done is the following. I've taken my C2, which is really the first fundamental representation of SL2, single box, so first fundamental or only fundamental representation, and I've formed this big tensor product. H is C2 L-fold tensor product. Now this setting is very important in representation theory because, well, we've already seen that on the one hand, SL2 acts on this. Whether or not this commutes with the Hamiltonian is another question, but now I'm not thinking about Hamiltonian, but just about the structure of the Hilbert space. So SL2 acts on here by S plus minus and SZ. And by the way, there's also the while group, which acts on here, which is just S2. And its action on the Hilbert space is precisely this spin flip operator. So this is related to my, did I call it U or V? I don't even know. It was U. U. Okay, very good. So this is where the representation theoretic interpretation of this U. But there's another action on this space because we just have L of identical particles. So one thing that you could do is you can just permute them. Let me call this orange for this side. So there's also an action of the symmetric group in L generators, which just permutes the spins. So this is the action which I call PIJ, swaps spins at sites I and J. And then Schur-Weil duality says that these two actions commute with each other, and moreover, if you want to know everything that commutes with this, you can express it in terms of PIJs, and everything that commutes with these PIJs, you can express in terms of S plus minus and Z. So they generate these mutual commutants. But this is related to Schur-Weil duality. And by Schur-Weil duality, this big middle representation is an extremely nice decomposition as a bimodule for these simultaneously. So it is, let's say, V lambda tensor S squared lambda, where this V is a highest weight representation for SL2. And we know that they're of the form, I can just write them as, well, we know that they're d-dimensional. And they look like this. They look like a string of dots, dot, 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 this. And then we have S plus minus going up and down. So here's S minus going down, S plus going up, and Z acts by eigenvalues. Those strings are precisely the strings that I had there. So these strings here, they're just the highest weight for SL2s. And then here, these guys are called Specht modules. They're irreducible representations of symmetric group, and they're labeled labeled by standard Young tableaus. Sorry, standard Young diagrams. No, sorry, the basis is labeled, that's what I want to say, excuse me. So they're labeled by this lambda, this partition, and the basis is labeled by standard Young tableau. If you know what that are. And if, in fact, we know that the dimension, sorry, let me write this. So the dimension of this flat module is, of course, the number of standard Young tableau of the shape lambda. And this is L choose M minus L M minus 1. Where again, so now I have to tell you what I sum over. So I'm summing over all the possible partitions of the number n, such that the length of the partition is at most 2. The n comes from this side and the 2 comes from that side. I guess I could, this condition is the kind of the SL2 condition, and the being a partition, so all the lambdas have to add up to n, is what it means. And concretely, what I do, oh, sorry, n is L. And concretely, it means that I can just write my partition like this, where the highest weight condition says that it should be lambda 1 should be larger than or equal to lambda 2, and this is this condition that m should be at most L over 2 to the equator condition. And so where are these FET modules in the picture? Well, in terms of just the representation theory, so now I'm going away for a moment again from the Hamiltonian. There's a trivial representation here. So it's one dimensional, and there's a copy here, there's a copy here, there's a copy here, there's a copy here, there's a copy here. Then we get what is called the standard representation. It is this line connecting the 3 red dots. It's also sitting here, and another copy sitting there. And then finally, here there's another representation, which is 2-dimensional, looking like this. In terms of standard Young tableau, this first part is my 1, 2, 3, 4. The next part is 1, 2, 3, 4, like that. And this one is called the window diagram. So you can check that the number of standard Young tableaus matches the dimensions that I was giving before, like that. So this is the L choose M minus L choose M minus 1. That's its length. Here, that's the dimension. Now, okay, this is all good and well, but we were interested in physics. So how much does it relate to our Hamiltonian? Well, it relates a little bit to it. So inside SL2, we have the Cartan algebra, H, which is just spanned by SZ. It also acts on here. And then instead, I can only look at representations of the Cartan algebra, which is precisely my decomposition into these weight modules, which are my horizontal lines. So maybe I should write this above actually, so that I have a little bit more space. So in here we have Cartan, and this space also decomposes in terms of Hm, which I told you now I should really write L minus M comma M, and 0 to L. So these are the irreducibles for this part here, which x by s by eigenvalues. That symmetric group, so it's spin permutations, it does not commute with our Hamiltonian. Because our Hamiltonian only, it has nearest neighbor interactions only. So if I can permute two spins to make them very far apart, they wouldn't interact anymore. So this clearly does not commute. So what does commute is the following. Well, we had our translation thing. So this is a copy of Z modulo LZ, cyclic subgroup, like that. But there's a little bit more because we also had parity. So this is this thing here. It's the semi-direct product of S2. This is parity. So we call it phi. And this here is G. And this together is just a dihedral group. Which makes sense, right? We think of well, the picture that I just erased. So we think of the chain. We look from the top now. We have all these sides like that. And we think now of the kind of N or L gone. And all the symmetries, well, we can either flip it like this, which was our parity, or we can rotate it like this, which was our translation. So that's the dihedral symmetries of the chain. They're just space kind of symmetries of nearest neighbor interacting Hamiltonians. And here this was extremely nice because it's a multiplicity-free decomposition. If you take into account both SL2 and the symmetric group, then there are no multiplicities. Each of these summands occurs exactly once. If you forget about the symmetric group, then this one occurs exactly dimension this many times. Whereas if you forget about the SL2, then this Specht module occurs precisely dimension of this many times. But if you think of them both together, then they were multiplicity free. However, if we now only restrict ourselves to the Cartan and to this dihedral subgroup, then it still decomposes, but not into there are multiplicities. Namely, not for m is 0, not for m is 1, because then everything was fixed by the momentum, but from m is 2 onwards, there are states that have the same energy and maybe even the same momentum, or sorry, not the same energy, but they have the same momentum, so we cannot just use this dihedral symmetry to completely decompose what we're doing. There is one model, sort of a spinching, which really fit in this Schur-Weil type of picture, and that is the mean fields model, where you just let everybody interact with each other in the same way. So what you can do is instead, you could consider the Hamiltonian, let's say, in the sum of Hij, j, all I less than j. Oh, maybe I should decide to call it k now. That's all possible sides k and l up to l. This one, now we made everything completely symmetric. So now I can swap around sides as much as I want, and the Hamiltonian doesn't feel it. This is a mean field model, so it's kind of boring. If you think of it in terms of if you want to draw the interactions, then we don't just have nearest neighbor interactions like before, but we have also next to nearest neighbor and so on and so on. So this is the complete graph. Some people like to think about Heisenberg models associated to graphs, and here we were thinking about Heisenberg spin chain associated to just a circle graph, whereas here we are thinking of the complete graph. And in this case, this decomposition is really, these are eigenspaces of the Hamiltonian. So you immediately understand them from Schur-Weil duality. Of course, you might say it's mean field, so it's a bit boring. It's also, by the way, it's also the quadratic Casimir in terms of SL2. So again, a little bit boring, but physically this is a bit relevant because in quantum computing there's this quantum computer called D-Wave, and they precisely try to engineer qubits that interact with each other all at the same time. So this would be kind of the physical model, the model underlying that quantum computer. And moreover, since there's extremely good control over the representation theory here, so you really understand all the energies and all the degeneracies completely and explicitly, in this case, you can really nicely do the analysis for it. So you can send L to infinity, and in this case, I mean, as a physicist, you would say it's trivial and we understand it, but if you're more mathematical, then here you can do it rigorously. So normally, sending L to infinity is exact, maybe, but not rigorous. But here you can really do rigorously, you can prove that for delta this, there's such a phase, for delta that, there's such a phase, there's a transition in between, and you can really properly prove everything. So mathematically, this is kind of fine.
How does that presentation theory help in this case? Basically, what is special about the Hamiltonian in this representation theory point of view? I could have used the same word if I did kind of Hamiltonian, which comes with a Z and is that hero group.
Absolutely, right.
So something has to be special.
No, nothing. The values of the energies which will occur. That's a special effect.
So
this is effect true for many more Hamiltonians. That's right.
So as long as spin chain to this outside, and that the Hamiltonian which commutes with a Z by more or less exactly solid using this method.
Whether or not beta ansatz works, that is depends on the Hamiltonian. But the representation theories, the dimensions, and so on, this we can sort of understand from this picture.
But the idea was supposed to be this theory while the beta ansatz.
No. This is just the representation theory in the context of this picture here. And then we go physics. So we choose our Hamiltonian. Then we have to, they're not degenerate like this, so they're irrelevant. If delta is not 1, then they're not degenerate according to those. So you have to forget all these grid lines that I drew. And this decomposition is useless, but at least maybe this one is useful. And then the fact that there are joints, the decomposition of this Hilbert space into bimodules for the parts that we are symmetric under still has multiplicities. That's the takeaway message. This is the mathematical version of saying this statement. That for m is 2 onwards, representation theory is not enough. Details will depend on the model, and we have to be smart. And for XXZ, we're lucky it's possible to do this, and beta will tell us next time how. Any other questions?
Question? No? Online, do you have a question?
Just the multiplicities in the case where you reduce only the lower symmetry.
This can be obtained as some representation theoretic data as well. I guess evaluation of some polynomials, like in Cassian-Lucid.
Bigger symmetry, yeah, I mean, then you have all the Schur polynomials showing up. For the smaller symmetry group, I mean, probably. I have not thought about it. It's sort of the same question as how do you compute which momentum occurs how often from n equals to 1. So you can, so it's kind of representation theory of this, you know, this, if you fix an m, then you can kind of think of a, but you don't really care about flipping the thing or translating it. So this is called the bracelet. So the different things that are different, identifying translated or flipped versions are called bracelets. You can count how many there are and so on, and then you can do the combinatorics of where the downspin sits precisely, and that would give you the answer of which momenta occur how often. But I don't know. It's an abstract way. I don't know if right. So I don't know. I mean, probably. So physically, it's kind of a nice exercise to do, but mathematically, I don't know if it's kind of nice enough that people have done it in detail. Maybe, probably. I mean, surely it cannot be super hard, but you know, it's yet another way to ask the same question. This exercise, the combinatorial exercise. All right.
Okay, thank you.